welcome everybody. Welcome to the part one of the rise and stall of the piston engine, the precursor to the big story of the Titanic and the Hindenburg. And in part one, I'm going to cover a very, very important subject, the subject of gasoline, water, and methanol, and what is the relationship. It's a very important relationship. It's one that's conveniently left out of today's discussions by the oil industry. Let's take a look at, first of all, what gasoline is. You notice that I describe it as the worst possible fuel that we could be using. The reason for that is that it has such a wide boiling range. And the boiling range is 130 degrees Fahrenheit to 430 degrees Fahrenheit. Well, because of that, it vaporizes very poorly, because it has such a wide range of differently sized molecules. Let's understand some important things about a liquid fuel. No liquid burns until it first boils. The 130 degree Fahrenheit fraction of gasoline thus is the first to burn in the cylinders. And the rest of the fuel, like up to 250, burns later, and then from 250 degrees to the 370 degrees, that fuel basically burns up in the tailpipe. This is why we're losing fuel mileage. This research, by the way, is thanks to Bruce McBurney. I would suggest you Google him and read his entire article and how he researched converting, well, we'll get into it, but he researched how to actually convert gasoline into methanol. Okay, so now let's take a look at methanol. There's three types of methanol. I'm sorry, there's three types of alcohol. There's methanol, ethanol, and isopropyl alcohol. Actually, there's a lot more alcohols than that, but we're mostly familiar with the first three. And you'll notice that as we go down the list here, we add carbon atoms. The first, methanol, is the lightest alcohol. It's just got one carbon atom. Ethanol has two. Isopropyl alcohol has three. Now, what you may not know is that methanol alcohol is actually made from the reformation of petroleum. It's primarily made from methane gas. Ethanol is the one that's made with fermentation, and that's the one that we're familiar with for our drinking purposes. And the last one, isopropyl alcohol, which is a three-carbon alcohol, basically used in hospitals and for wound dressing and things like that. Now, I might add that all beer and wine contain some methanol. Therefore, methanol is not poison. You can read this right off of Wikipedia or Google wine and beer contents. Read it for yourself, but they have made methanol out to be poisonous when in fact it is not poisonous. We're drinking it every day. Now, how do we make methanol? You might be surprised to know we can make it out of methane gas. This is the most common way. It does not come from corn stalks or food stocks of any kind like that. This is an industrial product made from an industrial feedstock, and in this case it's generally methane gas. Now, you notice looking at this methane molecule, and then looking over here at this methanol molecule, the only difference is one oxygen atom. Instead of having the H out here, what we have is an OH. That's the only difference, is that instead of having a regular H here, now we've got an OH here, an OH. So what do you need to make methanol? You need methane gas, and you need oxygen, and that's all you need. And where do we get oxygen? Okay, so we know that methanol is readily available. Natural gas is a feedstock used. Methanol is primarily a liquid petrochemical, and it's made from renewable. I said fossil fuels. Oops, I goofed. Let's just call those petroleum fuels. I don't believe the fossil fuel ruse. And that contain carbon and hydrogen. That's really what you need to make methanol. And methanol, as I mentioned, is the simplest alcohol. It's colorless, tasteless, and it's commonly known as wood alcohol. And this is the stuff that when you drink, I think makes you pretty crazy. I've seen in third world countries where I think they were feeding the natives methanol, and boy, does it mess them up. Okay, methanol, the formula, chemical formula is CH3OH, and I might add that stranded gas can be monetized by producing fuel-grade methanol and transporting it to market. So when you see this going on, you know something's wrong. All of this that they're allowed to flare off in the fields, they could be converting that into methanol. They could also be converting it into ammonia, NH3. And you might be surprised to know that our ammonia that we use for fertilizing our croplands in the United States comes from Australia, and it's made in Australia from natural gas. Why they don't make it here out of our natural gas, ask the oil company. They like to make it in Australia, ship it all the way here. We have ammonia. Hey, and guess what? We don't know where it came from, and they like that just fine. They bring it all into Port Arthur and they transport it via pipeline into the Corn Belt. Okay, back to gasoline. Gasoline is a very odd product. I mentioned it's got this wide boiling range, and as a result, a lot of the molecules don't look like that other molecule I showed you. They're actually in rings, like a benzene ring, and then these benzene rings sometimes attach to each other and produce olefins and cycloalkanes. So you get this is just one of hundreds of different chemical formulas that you will see for molecules coming from gasoline. It has such a wide range of molecules you wouldn't believe it. Well, as a result, it doesn't burn evenly, and it's also horribly polluted, and it contains what's known as volatile organic compounds. They're listed here. There's 17 minimum. These are all very toxic. And what do they say when you contact the Department of Air Quality? What do they say about the exhaust emissions of these VOCs? They say the combustion process results in emissions of volatile organic compounds, oxides of nitrogen, particulate matter, and carbon monoxide, which are released from the tailpipe while a vehicle is operating. So, in a way, it's just admitted that your catalytic converter does nothing for these. And that's the problem with gasoline. It comes out of the ground, and whatever comes out of the ground is horribly toxic. Okay, let's discuss water for a second. Water, chemical formula, H2O, looks kind of like this. Here's your big oxygen atom, then your two hydrogens. Now, when you break water apart, if you just break one bond, you notice you get a hydrogen and you get an OH. Now, that works out particularly useful when you're going to combine water with gasoline. What? Combine water with gasoline? Yes, that's what I said. Notice that they're, for example, let's say we take a octane molecule of a typical size would be C8H18. We could break that into 7 CH3OHs plus 1 CH4, and that would require 14 additional hydrogen and 7 additional oxygen, or 7 parts water. Let's take another look at this. We've got an octane molecule, and we're going to break the bonds in this point here, okay, these points here. And when we break this bond, we're going to need a hydrogen on one end, and we're going to put an OH on the other end. And that's just what we get from water. We get a hydrogen, and we get an OH when we break it, just one bond. And that is very possible to do. And you can get this reaction to go off. You can make methanol from water and gasoline by breaking it, such that your final equation results in 7 parts methanol and 1 part methane. You get some methane gas. Now, what's very noteworthy here is that you're going to end up with 4 times the original volume of gasoline. And you're going to need about 2 to 2.5 times as much gasoline as water to complete the reaction. this is a reaction they don't want us to know about, believe me, and they don't want to do this because this would multiply petroleum volume substantially. This is not an easy process. It's going to require temperatures above 900 degrees Fahrenheit. That's when water starts to become unstable. And no, they didn't teach you that in college. I realize that. And it's going to require pressures up there around 1,000 psi or higher. It's also going to require some catalyst. So it's not an easy process. But they do this in the reformer. They do this in the catalytic cracker every day at a refinery. And they can do this. It's very doable. Let's take a look at a methanol production flow sheet. You notice that they've got natural gas coming in here, and we've got air coming in over here. They don't want to show us that water is also coming in. But if you look real closely, you can see there's water. There's water exchanging here. Well, there has to be, because you're going to need twice as much water. You're going to need a lot more water than you do gas. So, I mean, it's a great reaction. It's a great way to multiply petroleum products, petroleum fuels, etc., and that's why they won't do it. They won't do it because they're going to get 4 times the original amount. Now, here's another reason that they won't do it. If we had methanol in place of, rot gut gasoline, where we're running like 8 to 10 to 1 compression ratios in our engines, we could increase these up to 20 to 1. Yeah, methanol and alcohols can run the higher compression ratios up there with diesel fuel. That would allow us to use engines that are about a quarter the size. Now, I might add, there's another reason why you can use a smaller engine, and that's because methanol has that oxygen atom in there, and that helps oxidize the fuel. So the air is actually coming into the engine in a liquid state when you run it on methanol. So we could have engines a quarter the size, because methanol put out about twice the horsepower. That's why they use it at Indianapolis. That's why they use ethanol in Indianapolis. It's oxygenated fuel. So your engine doesn't have to breathe as hard. It doesn't have to ingest as much oxygen, as much air. And that's why you can get much more power out of these small Indy engines. It's because they're using an oxygenated fuel. They don't like to mention that. Imagine in your hybrid car, if we, instead of a 4-cylinder engine here, we just use 1 cylinder. 0.8 liter. That's all you need. That's all you need. By the way, it shouldn't be a piston engine. It should be a Wankel engine, and those prototype cars are available. You can look at them, and eventually we'll have a small Wankel running on methanol. That's my prediction. That's the way I want to go with this for the interim period before we go all electric. So if we were to get this technology, if the oil industry would give it to us, we could reduce consumption of gasoline by 75 to 80%. And I might add that we can do this. We can use existing engines and automobiles. We can convert these to alcohol very quickly. And some of them will require some software updates and some retrofits, definitely. But this is very doable, and we could be totally non-toxic in a month, literally. We'd have no VOCs, no carbon monoxide. You could literally drive your car into your house and leave it running for a while until it sucked all the oxygen out. You wouldn't even notice. We'd have no smog. We'd have no polluted rivers and lakes. And that's my purpose. That's why I'm presenting this, because this is mind-boggling information, and in the mind of the right person, who knows what could happen. Another advantage of using methanol is that it mixes with water, and you can actually produce more power if you mix about 10% water with it. Well, let's take a look at an example. One of my favorite is the Mark 14 World War II torpedo, which used methanol. Now I'm showing you where the turbine is. This was a turbine powered, running off methanol. One wheel went one way, the other wheel went the other way. This is just an impulse turbine, but who cares? It's under so much pressure. It's so compact, it doesn't matter. One's going one way and the other another way. So we get two shafts going here in a set of gearing. It's the most amazing set of gearing I think I've ever seen. But anyway, we get two counter-rotating shafts so that we have the counter-rotating propellers. And to get this thing fired off, it's got a pressurized air tank. So when they light this thing off, it's already at 500 psi. That helps the methanol burn quick, with lots of power right off the bat. But here's the mind-blowing part. Oh, by the way, here's the turbine. Here's the turbine right here. This is a 21-inch torpedo, and you can see this is a very, very compact engine. How does it work? Here's the igniter. Notice that you got water in, we've got fuel in, we got air in, and we've got the igniter to set it off. And that's, there's a schematic of how it works, the three ingredients, very simple. But when this goes off at this pressure, it immediately boils the water and turns the water into superheated steam. So you're actually running this turbine off of superheated steam just from this flask, and you never had a steam boiler. So I mean, what an amazing device. When I first saw this World War II torpedo, I couldn't believe it. Three ingredients: air, methanol, and water. Here again, it's showing the combustion flask and how it goes up, and here's the nozzles. Very simple. And anytime they tell you they can't make turbines because of manufacturing problems or etc., it's just not true, because they made literally hundreds of thousands of these during the war. So they can manufacture turbines. There's no problem at all. Let's take a look at some other turbines. Here's the Chrysler turbine. And I'm just showing you this because I'm on the subject of turbines, and I just guess I really like them. Here's a shot of the engine, and this ended up going into the Abrams tank. We didn't get the car, but the military got the engine. That's what they put in their tank. You can see it's not that complicated looking at all, really. And it's really a much more simple engine to build than a piston engine with all its, but they make it sound like it's very difficult. Well, here's another example, the 1967 Indianapolis turbine car that Parnelli Jones drove. Came within, what, 1 or 2 laps, and then, it went into neutral. Okay, yeah, it went into neutral. All right, yeah. Well, I believe that story. I believe that until 1968, when there were 2 turbine cars leading the race, and both of them shut down at the same time. I have that in my book. You can read it. It's amazing. They shut both of these cars down 3 laps from the end, and they both shut down for the same reason. They said the fuel pump shafts sheared. Well, what are the odds of 2 fuel pump shafts shearing at the same point in the same race? Come on. Come on. I might add that this thing didn't need to run on gasoline. They were running gasoline at that time. I think they might have been on methanol then, but I believe they were running gasoline. This thing could run on diesel fuel because turbines run better on diesel fuel, like jet fuel. And it actually didn't need to make a pit stop. There's no way they're going to let this car compete. I mean, think about it. This is the biggest showmanship event of the year in the United States, or maybe the world, the Indianapolis 500. It's all about pit stops, getting in and out. Can you imagine trying to take that out of the race? So that's why we ended up with pistons. Here's the 1968 Ford Coyote engine, which A.J. Foyt said he thought that the turbine had about twice the power of his car. That's what he said. And he said, I'm willing to go to turbines, but, you can't have them both. And that's true. They're just so much more superior. So anyway, I just wanted to make a few points about the turbine engine. But the fact is that we are still using gasoline when we shouldn't have to. What's the result? Unnecessary drilling. We didn't need this. Here's Long Beach in 1936. Long Beach, California. Prime land to live down next to beautiful Pacific Ocean. Fishing, outstanding, surfing, sunbathing. We didn't need to have reckless fracking, which is what's going on right now. There's no excuse for this. There is a huge environmental impact when you frack. And look at all these chemicals all these different tanks and everything that they bring onto your property because they have the drilling rights, they have the fracking rights. You can't stop them. They're going to come onto your property, and look at how many people's properties they've gone onto. I mean, you can look, the whole United States is practically covered like this. I mean, it is unbelievable. Fracking is way out of control. If anybody says petroleum's good, just use one word. No, it's not. Why not? It's because of the word fracking. It's the worst environmental genocide they could have ever come up with. We also never needed to have uncontrolled oil platform developments in the Gulf. I mean, look at this map of all these platforms that exist today. How do the fish survive this? I don't know. We never needed to have reckless deep ocean drilling. We never needed to have the Deepwater Horizons without its blowout preventer cause this environmental disaster. We could have all along been using a totally non-toxic fuel and not polluted our rivers and lakes if they had just allowed us to convert our petroleum products, whether it's a liquid or a gas, by converting it into alcohols. We would have had no dependence on foreign oil. So that concludes my first part on the rise and fall of the piston engine. My name is Kenneth Price. I thank you very much for listening, and I hope I see you in the next episodes. Thank you.